Hi guys, welcome back to the channel. In this video, I will be going through the Equilibria topic of the A-level chemistry curriculum. So let's begin. So first, you need to know that many reactions are reversible. So if a reaction has this sign, this is a reversible sign, and this indicates that the reaction is reversible. And for a reversible reaction at equilibrium, there are two conditions. And the first condition is that the forward and the backward reaction occur at equal rates. So in this example, the forward reaction, which is making the product, occurs at the same rate as the backward reaction, which is making the reactants. Now the second condition is that the concentration of the reactant on the product remains constant. Now it's very important that you use the word constant, because the concentration reactant in the product may not be the same, but the proportion of the amounts will be the same. That's why you say constants and not same. And you should know Le Chatelier's principle by heart, and it is: if conditions of a system in a dynamic equilibrium are changed, the position of equilibrium shifts to counteract the change. Now learn this principle really well, because it has been tested a lot of times in the past. Alright, so the effect of temperature on equilibrium. So there is a structure of mark points that you should know, and I'm going to be going through that now. So first, what you should mention is if the forward reaction is endothermic or exothermic. So for example, in this case, this has a plus sign with the enthalpy change, so I know this will be an endothermic reaction. If it had a minus, I would know it's exothermic, and I would start by mentioning that the forward reaction is endo or exothermic. And then I will say, oh, the temperature is either increased or decreased, and I will then say that the equilibrium would shift to oppose that change. So for example, in the first instance, if the temperature was increased, then I would say that the equilibrium shifts to oppose that change by decreasing the temperature, and vice versa if it was a decrease in temperature that happened in the first place. And then I would say the equilibrium shifts to the right or left direction. I can also say if it'll shift in the endothermic or the exothermic direction. Now this depends on the equation, but we'll be going through an example later on. And then finally, if it's asking for what would happen to the yield of a product or a reactant, it might mention a specific reactant or a product. Then I would say that, oh, yield of this product or reactant increases or decreases depending on the reaction. So I'll take this question into account. So what happens to the yield of NO2 if the temperature is increased? So this is the reaction. Now I know this is endothermic, and I have the reactant N2O4 making the product 2NO2. So I will start off by saying that the forward reaction is endothermic, as it has a plus sign with the enthalpy change. Then I would say that the temperature increases, as it's mentioned in the question that the temperatures increase. So I would say temperature increases, so equilibrium would shift to decrease temperature. So the equilibrium shifts to oppose that change, and by opposing that change, it should be decreasing the temperature. And then I can say that the equilibrium shifts to the right side, because obviously you're increasing the temperature, and this would be moving the equilibrium towards the exothermic direction as you're increasing the temperature. So this would be moving it towards the backward direction. So to oppose that change, to decrease that temperature, you should be moving it towards endothermic direction, as obviously that would require energy, that would absorb energy and decrease temperature. So equilibrium would shift to the right side. I can say it would shift in the forward direction, and the yield of NO2 would decrease, and as the equilibrium is shifted to the right side, more products will be formed, so the yield of NO2 would increase. So this is the structure of answering this type of question. So effect of concentration or pressure on equilibrium. So what you should have in mind is when the word concentration is used, it's usually with a solution, so aqueous, but pressure is always with gases. And again, if volume increases, now they might trick you like that. So if volume increases, what happens to the pressure is the pressure decreases, and it's the other way around. So if volume decreases, the pressure increases. So keep that in mind. So just as an example, if we have this box and we have 3, 4, 5, 6 particles in this, and now this has a certain pressure. But now if we have to make this box bigger, but we still have 6 particles, so we have increased the volume. The volume has increased, but the pressure, if you think of it, now the particles have more space, and they will move. There will be less collisions, and they can move around more. So the pressure has decreased, and that's what happens with this. So don't get mixed up with them. If it says that something has happened to the volume, it will be the opposite in terms of the pressure, and we only talk about the pressure for gases. So again, the mark points for pressure now, or it's the same for concentration. It has the same mark point. So, but you would be talking about concentration instead of pressure when it's talking about concentration in the question. So what happens if there's a change in pressure, the equilibrium shifts to oppose that change. So these similar mark points to the temperature mark points. So then there will be an increase or decrease in pressure. So for example, if there was an increase in the pressure in the first place, the equilibrium, and there will be a decrease in pressure as the equilibrium would shift to the oppose that change. So equilibrium, what happens this time is it shifts toward the side with either more or fewer moles. So first in temperature we either had endothermic or exothermic, but with pressure we have moles. So if a product has more moles or the reactant has more moles, we would be thinking of that instead of the enthalpy change and the yield of X. So how would that impact the yield of X? Would that increase or decrease? So looking at an example, it's asking what would happen to the yield of C if the volume was increased. So I know this is talking about volume being increasing, so I know that the pressure is decreasing, so it's going down. So thinking of this example, I know that there are more moles of products than reactants. So because there's 1C and there is 3D, so I know there's 4 moles of the products. So this is how you work out the moles. But looking at the reactants, there is only 2B and 1A, so that adds up to 2. So 3 to 4, I know that the products have more moles. So that's what I would say in my first step. So there are more moles of products than reactants. So what happens is the equilibrium will shift to the right side to increase the pressure. So because the pressure is being decreased, we need to increase the pressure, and we would increase the pressure by moving towards the side with more moles. So because the products have more moles, we would move towards that direction. So this would be towards the right side to increase the pressure, and that's why the yield of C would increase. It's asking about the yield of C in the question. So because there will be more products being formed, the yield of C would increase. But sometimes they try to trick you. So looking at this example, if we're looking at the moles, we have 1, 2, so 2 moles of reactants, and there is also 2 moles of products. So what happens in this case? So remember that if the number of moles of reactants and products are equal, changing pressure has no effect on the equilibrium. So in this case, there's the same number of moles of reactants and products, so changing pressure will have no effect on the equilibrium. So how does the catalyst affect the equilibrium? So remember that catalyst has no effect on the position of equilibrium. So adding a catalyst wouldn't move the equilibrium to the right or the left side. What it does, it speeds up forward and backward reaction by the same amount. So it will increase the reaction rate, the forward and backward reaction rate, by the same amount. And that's why it ends up speeding the rate at which equilibrium is achieved, instead of changing the position of equilibrium. So it just speeds up the rate at which equilibrium is reached, as it's speeding up the forward and the backward reaction, because it's speeding it up by the same amount. If it was speeding it up by different amounts, then that would establish a position of equilibrium, but because it's the same amount, nothing happens to the position of equilibrium. All right, so compromise, you're required to know about the compromise. So for example, if higher temperature indicates a higher product yield, then why don't we use the highest possible temperatures? Why do we use lower temperatures? This is because higher temperatures would cost high energy, and therefore they would be expensive, and to save some money we would compromise by using lower temperatures. But if the lower temperature is the best, then why don't we use the lowest possible temperature? Why do we use higher temperature? This is because the lower temperature would, if you remember from the collision theory, it would cause a slower rate of reaction, as particles, there will be less collisions, therefore less successful collisions per second, leading to a rate of reaction. So that's why we use higher temperature, if the lowest possible temperature would give you the higher yield. So pressure, why do we lower the pressure when the highest pressure gives us the highest yield? This is because high pressure, again, it costs high energy and it's quite expensive, and also high pressure equipment is expensive to build and operate, and it's also very dangerous. And we use higher pressure when the lowest pressure would give us the highest yield, is because lower pressure, again, slow rate of reaction, and in an industry we would want faster reactions and to produce the products faster so we can get money quicker. So you're required to know a few things. So if I needed to write the concentration of X, I can write this in square brackets. So square bracket X, and that would indicate the concentration of X. And if X had 5 moles, then I could write the concentration by adding a power, which would indicate the moles of X. So if it was X having 4 moles, then I can just write X and to the power of 4, and this would indicate that there are 4 moles of X. So that's the coefficient of the equation. And so, for example, if we have this equation, these are the moles of each of these. So A, B, C, D in lower cases are the moles, and A, B, C, D in the upper cases are the actual reactants and products. We can write the Kc equation by the products over reactants. So the products go on the top, reactants go on the bottom. So we would write the concentrations of each. So again, products first. So C is the first product. The moles of C are the lowercase c. So that's how we would add each of the. That's how we would write the equation for Kc. All right. So the equilibrium constant, or the Kc. So that's a constant of concentration, and the value of Kc is unaffected by changes in concentration or addition of a catalyst. So if you change the concentration, or if you add a catalyst, the value of the equilibrium constant, or the Kc, and the equilibrium constant of concentration would remain the same. But the value would change if the temperature changes. So Kc changes if the temperature changes. All right, so now looking at the Kc examples. In this question, we've been given the equation, and we've been given the concentrations for each of the reactants and the products. and we've been basically asked to calculate Kc. So how do we start this? What we would do is we would write the Kc equation first. So as we've written before, and the products will go on the top, so it'd be square brackets and CH3 and COO CH2 CH3. So this is one of the products, and this would go on the top, and the other being H2O would also go on the top. So next we have the reactants, and this would go on the bottom, so that would be CH3 CH2 OH, and the other one is CH3 and CO COOH. So none of these have any coefficients of more than 1, so that's why I don't need any powers in this. So then we would write the values. So we've been given the concentrations for each of them. So now we've been given the concentrations for all the reactants and the products. So what we do is we simply replace the concentrations with all of the reactants and the products. So starting off CH3 COO CH2 CH3, and we've been told that this is 0.10, so we've just put 0.1, and we can put that into square brackets, but these are basically timesing, and the other ones again, H2A is 0.1 as well. I don't need to put it into square brackets now, but I'm doing it just so you understand that these are still concentrations. And then we have the reactants, which is 0.4 multiplied by 0.4. So what we get from these numbers is 0.0625. This will be the Kc value for this particular reaction and this particular temperature. All right, so the units. So if I say we have this reaction, we can also be asked to work out the units for the Kc. And so what we start off by is we just write the Kc equation. So for this reaction, it's Kc SO3 squared, because there is a coefficient, there's 2 moles of SO3 over SO2 again squared, because there's 2 moles of SO2, and O2 has only 1 mole, so we don't need any powers on that. So then what we do is, because I know all of the concentrations are in moles per decimeter cubed, so I can just write that down. So I can say, oh, the products, it has moles per decimeter cubed, and then because I know it's to the power of 2, I would put that is to the power of 2. Now I know the reactants, so for example SO2, it's to the power of 2, and then we also have O2. So if we are looking at all these moles, it's 2 plus 1, which is 3. So that's why when we write the reactants concentration, that will be to the power of 3. So because these are the same concentrations, what we can do is cancel these out. So because we have 3 at the bottom and 2 at the top, we can cancel all the top ones, and we would be left with 1 on the bottom. So it would just be 1 over moles per decimeter squared. So then if we want to move this to the top, what we do is we would say that this is moles to the power of -1 and decimeter cubed. So the sign basically reverses. So because it was +1, so it was basically moles to the power of 1 decimeter -3. So the sign reverses, so it becomes moles to the power of -1 decimeter cubed, and this is how you would write the units for the Kc. Now if there are equal moles on both sides of the equation, then there will be no units. So for example, looking at this equation, we can see that there's 2 moles of reactants and 2 moles of products. I know this will be moles decimeter cubed to the power of 2 over moles decimeter to the power of 2 again. So both of these cancel out, and we would just be left with 1. That's why we don't need any units. So as soon as you see equimolar. As soon as you see that the reactants and products have same number of moles, then you don't need to do any working. You just simply know that they will have no units. Alright, so moving on to more complex questions now that you can get with KC. So in this question, we've been told that we've got 6 moles of SO2 and reacting with 2 moles of O2 at 450 K, then that's the temperature, and 2.5 and in a vessel of volume 2.5 decimeters cubed. And at equilibrium reaction, the mixture contained 4 moles of SO2, and you've been asked to calculate Kc and give its units, and we've been given the equation. So this is not as simple as what you may think, and there is a lot more working to it. So what we would do is simply, for any question, you would write the Kc and the equation down. So the simplest in terms of the atoms and the compounds that we have. So it'd just be SO3 squared, because again there's 2 moles of SO3 in this time, so over the reactants, so SO2 squared and O2. So then for this question, what we do is we use something called ICE. So this stands for initial moles, change in moles, and equilibrium moles. So just remember this. So starting off, we know that there are 6 moles of SO2. So starting from reactants to products, so SO2, I can say that initially we have 6 moles. And we know that it's reacted with 2 moles of O2, so we can write 2 moles of O2. And any product starting off, it would have no moles, unless it's been stated in the question that it has 2 moles or whatever. We can assume that it will have 0 moles. And then we've been told that equilibrium, that the reaction mixture contained 4 moles of SO2. So SO2 at equilibrium, we've been told that it contains 4 moles. So remember that this E stands for equilibrium moles, and we've been told that this is 4 moles. So this is what we can use to work everything else out. So in this, we know that from 6 to 4, we would have lost 2 moles. So change in moles is -2. So then we take into account the coefficient of each of these. So the moles, the number of moles in the equation. So we know that the ratio from SO2 to oxygen is 2 to 1. So then we would know that the change in mole for oxygen would be the half of SO2. So this would be -1. So that's why it's 2 minus 1, we would have 1 mole left. And the proportion between SO2 and SO3 is a 1-to-1 ratio, because there's 2 moles on both of them. So we know that the products would gain 2 moles. So the reactants would be losing them, the moles, and the products would be gaining that moles. So we know from 0 to 2, so this has 2 moles. But this is the number of moles each of them have at equilibrium. But now we've been told that the volume is 2.5 decimeter cube. So all this we have is the moles, but we don't have the concentration. And for Kc, we need the concentration, not the moles. So then we need to find the concentration, and this is what we will need the equation of concentration equals moles divided by volume. So then I would need to calculate concentrations for each of them. So what I would do is just simply, I've got the moles for each of them, and I have the volume which has been provided in the question, which is 2.5. So I just divide all of the moles by 2.5. So 4 divided by 5, I know 4 divided by 2.5, sorry, so I know that would be 1.6 moles per decimeter cubed. This is the concentration now. 1 divided by 2.5 is 0.4, and 2 divided by 2.5 is 0.8. So these are all the concentrations now. So then what we do is we simply substitute all of these in, so into the Kc equation, because we've got the concentrations now. And and we should get the answer, which will be 0.625. And we've also been asked to work out the units, so the question isn't complete yet. So we know that there's 2 moles of the product, so we can just write moles per decimeter squared. And then we know 2 plus 1, there's 3 moles of the reactant, so we can just write cubed moles decimeter cubed per, and the whole thing's cubed. So then when we're cancelling out, there is it'd be 1 over moles per decimeter cubed, and that's why the unit for this would be moles to the power of -1 and decimeter cubed. And so the final answer would be 0.625 moles to the power of -1 decimeter cubed. And this is how you use ice to calculate Kc. Thank you so much for watching this video. If you did like this video, don't forget to subscribe to see more of these, and you can watch my recent videos by clicking on the links popping up. Thank you.